Good morning, everyone. We only have 5 minutes left to the noon. Thank you so much for taking the time and attending this session. My name is Elham Dolatabadi. I'm an assistant professor at York University in Toronto, Ontario, Canada, and also a faculty affiliate at Vector Institute. For some of you who haven't heard about Vector Institute, it's a pan-Canadian It's founded through Pan-Canadian AI strategy to accelerate the adoption of AI in Canada and also across the world. So we try to do real-world AI research. And in this talk, I'm going to talk about some of the initiatives that we've done at the intersection of foundation models, large language models, and healthcare, and how creating open resource initiatives can shift and transform health AI and to kind of from building infrastructure to making real-world impact. Okay, so let's start with this simple but very important question. How do we as human understand the world? And I want you to think about it from a multimodal perspective. So as humans, our understanding of the world is inherently multimodal. We just don't rely on text or image. We have this multimodal sensory perception that kind of understand, like we see, we hear sounds, we touch things, and we basically all of these information come independently and through their own modality. But our brain is capable of integrating vision, language, and sound, and even the context, and build a unitary representation. For example, imagine you're walking down the street and suddenly you hear a loud bang. And you also see a car just crash into a pole right in front of you. You see people, a crowd talking about it. You a bird might fly. So kind of many things could happen at the same time, but your brain is able to understand the context and integrate the information related to the car accident. But kind of the next question here is, how do models see the world? So this is very important because this is like all of the AI researchers, their mission is to make AI as as intelligent as human, also make them more intelligent than human. And they want to mimic the way that human brain works. And that's how, ML models or these large language models, foundation models, are built these days. But models, by contrast, don't experience the world. They pretty much interpret the world through data. For example, a vision model that is trained for object detection sees pixels. A language models like the translators or the translation machine or like chatbots sees the words, understands the words. And multimodals, on the other hand, try to connect these streams, like the text and pixels. So basically, but unlike humans, they don't naturally integrate information. We have to teach them. We have to design those connections for them. So here, let's take a look at how a typical vision language model works. Pretty much like the back end of vision language models that we are interacting these days. So we call them vision language models because they integrate only two modalities, but you can expand them to include more modalities. But vision language models are the most typical and well-established language models these days. The architecture has two main components: an image encoder. Just bear with me. So I'm going to see like if I can, yeah. So there's a vision encoder, basically like that understands or include images and tries to learn a representation or an abstraction of the image. So it takes the image as an input, and also there is a language encoder which takes the prompt, the instruction, and understands that instruction and encode it into a representation. And next, as you see, basically like this is our image encoder and this is the instruction. For example, I can read it loud for you. Choose the correct option to the following question. Which picture shows the pizza inside the oven? Left one, right one. So we have basically two pictures, and this is the question. And we want the language model to respond in a language. So the images will be inputted into the image encoder. And then this is the instruction, as you see here. So basically, like there is an encoder that learns a representation from images, and this is the instruction that goes into the text encoder, and there is a cue former here as an example that through an attention process tries to bridge the image features and language queries, enabling the language model to generate context-aware responses. So long story short, through these encoders, we can learn representations from each modalities, and then those representations will be combined and concatenated, will be inputted into the language decoder, like the ChatGPT, and this way it provides a response to us. Something that I want you to basically want to highlight here is that the progress in this space often comes down to designing better encoders. So in this context, like designing better vision encoders is super important, and by better image encoder, it means that the stronger the image encoder gives us representation, and better image encoder gives us better representations of the image. And it means that the better the representation, the better the downstream applications or performance could be, for example, on retrieval and classification that I will show you next. So, okay, so the question is like, okay, how can we build a strong representations? And a major leap forward came with CLIP, which stands for Contrastive Language Image Pre-training. So what I would like to ask the audience is, how many of you have heard about CLIP models? Okay, just a few of you. So CLIP has been introduced by OpenAI, and it's fully open source, and it's a way, basically the idea is very simple but very powerful. So what we do with CLIP is it's a training mechanism or a strategy that helps us to train powerful and align image and text in the same embedding space. For example, let's say that there is an image, and the image has its own caption. So what we try to do is we train our neural network in a way that images and its corresponding caption are aligned in the embedding space. So this way, our representations are very powerful and can help us with doing retrieval tasks, for example, for a given image, using the encoders that are trained through contrastive learning. We can assign it to its own caption, and vice versa. And the way it works that through training, through the training strategy or mechanism, the aligned images and text are pushed together, and basically the ones that are not aligned are pulled. And this way, the model, the encoders are trained to they're trained that images and text that are aligned, also they in the embedding space, they're also aligned and have a shared embedding space. As you can see, so the blue ones are the aligned ones, and these ones are these images and text are not aligned. And the model learns a shared embedding space that the aligned images and text are falling together. So now the next question is so this model, like clip training, is very powerful, which means that in a zero-shot setting without any training, through using the encoders, you can find the corresponding text or image. But the next question is what data set did they use for training? And CLIP model was made open source in 2021, and they used 400 million image text pairs to train the model. And of course, these advances depend heavily on data, and that inspired the creation of even larger open data sets, like Lion 400 million and also 5 billion. So they curated 5 billion image text pairs, which is huge. And for researchers like me in the medical domain, the question is okay, so a scale helps with making these models more powerful. So they started with 400 million. They scaled it up to 5 billion in 2022. Okay, so in the healthcare domain, the story is a bit different. So we don't have this, we can't leverage large amounts of data. So the health data is fragmented. It's usually within the hospital walls, and making having 5 billion image text pairs is totally impossible. So given the success that people saw in the natural domain, for CLIP in the medical domain, they also started building image text pairs so they could leverage for training encoders, vision encoders, text encoders for medical tasks. For example, for a given image, what is for example, you provide the model with an image of a chest X-ray radiology, and the question is okay, what is the diagnosis? Is it pneumonia or pneumothorax? So these are some of the problems in the medical domain, and basically researchers were interested in solving or training models for these tasks. So they started building image text pairs. So the first one was the ROCO dataset, but they only had 80,000 image text pairs. Then PMC-OA scaled it to 1.6 in 2023. Then Biomed Clip by Microsoft, they scaled it up to 15 million, but it was not open source. They only released the checkpoints, not the data set itself. And later on, by Biomedica, if I'm not mistaken, by Stanford, they scaled it up to 24 million in 2024. So again, we saw that basically they tried to scale it up as just to make it, trying to adopt CLIP model in the healthcare domain. But the next question was okay, so we're talking about the medical domain, the health domain, which is very different than the natural domain. So medical domain has its own challenges and difficulties. It's very unique in many perspectives. The modalities of the data, so images, we're talking about different modalities, radiology, visible light photography, as you see in endoscopies. We also have microscopic images, and also the way we don't have captions. We usually have reports written by clinicians. So basically, adopting CLIP for medical domain has its own challenges. And so this question became basically a research question for us, whether bigger always better. Like, okay, so if we want to make successful integration of CLIP models in the medical domain, should we just scale the data? Is it like the data quality? Is it the data quantity or the data quality? So through literature, we learned that the scale matters, but in medicine, data quality, filtering, annotation often matter more than the kind of the volume. And otherwise, we risk models learning noise, artifacts, or biases that could impact patient care. So the stake is pretty high. So this is the research question that basically we tried to answer. And to answer this question, we curated our high-quality image-text pairs. We call it Open PMC. It's been accepted at MICAI, which is in a few weeks from here. And what we did was we curated 2.2 million image-text pairs for the medical domain, but with high quality. So when I say high quality, what does it mean? Basically, like, does any of you, so when I say like, okay, something that I forgot to mention here was, okay, I talked about PMC, OA, Biomed, CLIP. I forgot to mention how they've been curated. How do you think they've been curated? So we are talking about millions of image-text pairs in the medical domain, and there's no way that we can get these image-text pairs from clinical data or like patients' data that are captured within hospital settings. How do you think we curate these data? The actual CLIP model by OpenAI, they curated like those natural images from the web. It was a web crawling. But for the medical domain, we don't do web crawling. We do publication crawling, basically like PubMed articles, the articles which are for biomedical domain. We extract images and figures from those articles with the corresponding caption. So, but that's not enough. So we cannot call it a high quality, because in the medical domain, or like when it comes to publication, in the medical domain, it's very common to have compound figures, like, there's a panel of figures, subfigure A, subfigure B, subfigure C, and once you extract them, you have to decompose them into subfigures. That's something that we did, but other studies, they didn't. And also, like the captions, they are not very, basically like once we decompose the compound figures into subfigures, we also need to decompose the captions and basically like to caption A, B, C, and also align them with the extracted subfigures. That's another thing that we did. Also, we found that captions are not enough for training image text pairs or training our CLIP encoders, because in the medical domain, for a given radiology, we have a full radiology report, but those captions, they cannot provide the full context. And usually the full context is within the body of the article. So basically, like within the article, they reference to the figures, and those references, which we call in-text references and summaries, they provide a kind of better story for the figures than the caption. So what we also did was extracting those in-text references and summarizing them and integrating them into the caption. So this way we can have a full clinical or biomedical report. And kind of that's why we call it a high quality data. So here, like I can show you some of the examples of the figures that we had in once crawling the biomedical articles. As you see, like, these are some examples of microscopic images. As you see, like, it's a multi-panel figure, and we also had plots that we had to filter out. Also here, like, as you see, like in this panel, we have a radiology which I believe this is a CT scan, another scan, and then we have microscopic images. So what we did was, through this subfigure extraction, we were able to decompose them automatically. Just better visualization. Also, like, this is the captions for the compound figures. As we also had to kind of decompose it and kind of for subfigure A, subfigure B, and also attach them or align them with the corresponding subfigure. And also, like, for example, this is an example of the article text that we were able to extract and attach to the figure, so to the caption. So basically, like, this is where we are. We call our data open PMC. It's we made it publicly available, publicly open. That's why it's called open PMC. And PMC stands for, like, PubMed articles. So in terms of the size, we are still smaller than PMC 15M and Biomedica. So kind of fivefold less, but we have summarized references, subfigures. It's medical only. We filtered only for medical only. We filtered out plots and other stuff. We also provide the modality information, and it's fully open access. So this is where we stand. So we did the clip training. We used 800 GPUs for that, and these are some examples to show you, like, the performance. So basically, like, what I'm trying to show you here is that data quality is as important as data quantity. So we are much smaller than PMC 15M and Biomedica, but our performance kind of when it comes to retrieval task, it's much better. So for the retrieval, is like you give an image to the encoders, for example, a radiology image, and you ask the encoders to find the corresponding text or report. And this is like the retrieval task. We don't do any training. We use the encoders in a zero-shot setting. Also, for zero-shot classification, for example, there is a radiology image. We ask it, okay, what is the diagnosis? Is it pneumonia, pneumothorax, COVID-19? And this is like the classification task. Again, we didn't do any post-training. Like, we use the encoders in a zero-shot setting. And as you can see, like, in radiology, our model outperforms other models. And in terms of, like, on the x-axis, you see the size. And as you see, like, we are much smaller than those two models, but we outperformed. And it's all about because, like, the data quality was taken care of. And so the question is, like, okay, so our the other question that we had, so I kind of go through them very quickly, mindful of time, is like, okay, we were curious to know, like, okay, did we learn a different representation in the embedding space than the other models like Biomedica or Biomed Clip by Microsoft? And the red ones, actually, like the blue ones are ours. And as you see, like, we, on the embedding space, we learn a different representation. And we also tried it, actually measured it statistically, and the differences were significant. So what makes OpenPMC superior is, first of all, is like the quality of the figures. And through, like, we did two things. We enhanced contextual knowledge by leveraging in-text summaries, and we did an ablation study, and we showed that learning kind of in adding in-text summaries matters. We also looked at, like, the other quality component comes from the subfigure extraction. We also did an ablation study, and we learned that it also matters too. So the second one was super important, but the next question was, okay, in a smaller scale regime like 2.2 million, we learned that data quality matters. What about, can we do it at a larger scale? So we scaled it up to 18 million. Now we have 18 million highly curated image text pairs. And we also have a preprint. It's under review, our paper now. And for this one, we tried to improve our subfigure extraction. So we trained an object detection model that basically for any given compound figures, if it's a kind of a multi-panel complicated images, subfigures, it can basically decompose it into subfigures, because sometimes some panels are very complicated, like they're not symmetric, as you see here. For example, so all these microscopic images, not any object extraction model can decompose it into nice subfigures, but we trained our own object detection, subfigure extraction tool, and we were able to extract it, and we also made it publicly available, so any researchers in the field can leverage those. And we also basically measured its performance for the retrieval tasks again, and we showed that our model outperformed all the existing models and also our previous open PMC, which was on 2.2, and also the same results for the classification. It outperformed. So here we showed that, okay, so data quality matters, but also data quantity. I believe we still have time. So since we have time, okay, I can open it for question and answers. So just to summarize, okay, so the question here is why open medical AI matters for the open source community. So basically, it could be, there's a lot of discussions around this, and because in the medical domain, I'm doing AI for health. I've been doing it for the past 20 years, and we are still challenging with making medical data, clinical data that are captured within the hospital settings, open or accessible to researchers. It's within each jurisdictions or countries, they have their own rules. But to my knowledge, it's still very limited because we are talking about patients' data, we are talking about confidentialities, and medicine is high stakes, right? But on the other hand, the thing is, okay, so if we don't we see that AI models are becoming more intelligent every day, are becoming more powerful, and why can't we use these models for health applications? Because within the health domain, we are still facing many problems. The health data is captured with biases, and most of the diagnostics are biased, and also we are still kind of the rates of, if you look at within each I don't know the worldwide ratio, but I know that, in North America, more than 30%, there's a risk of misdiagnosis, underdiagnosis, which is huge. And also when it comes to equity, we are suffering from inequities in healthcare, and there is long wait times. So basically, there are many inefficiencies and problems and inaccuracies that can be improved with AI. But because this health data is not openly accessible by AI researchers, basically, health AI hasn't been improved, or the progress within health AI is much slower than the natural domain. And for students and researchers in these domains, if they want to publish, they can't wait. For example, sometimes getting access to data takes years. And think about a master's student wants to graduate in 2 years. So these are the big hurdles in the medical domain. That's why we try to create these image text pairs and make it publicly available. So open data and infrastructure let researchers, clinicians, and regulators verify results, check for biases, and build confidence in AI systems. And without reproducibility or transparency, models risk becoming, black boxes, and that basically clinicians cannot trust. Also, I talked about access and equity. Proprietary data sets are often locked to a few well-funded institutions, and this reinforces global inequities. And open resources democratize access, enabling researchers in low-resource settings to participate in innovative and kind of address local health priorities. For example, if we have access to hospital A data set and build a model, that model cannot be used for in other institutes. And there are still some, open data sets. For example, shared open data sets like Mimic by MIT in Boston. Also, I mentioned PMCOA and some other. They showed that how they establish common benchmark. For example, when it comes to electronic medical records, let's say in Ontario, we have Gemini, which is our electronic medical records coming from 30 hospitals that we researchers try to build models for various diagnostic and prognostic tasks. But we usually benchmark our models against Mimic. So this way, we can leverage some of the open source code bases that are built for Mimic, so we can leverage it for our own local hospital problems. And also, if we do something for our local hospital data and we show that it outperforms the models that are built for Mimic, we can also open source the code base and show that, hey, we were able to address some of the shortcomings with Mimic. So basically having this common benchmark, which is similar to ImageNet that we have in the natural domain for computer vision tasks, it accelerates, progress and by allowing fair comparisons and collective improvements rather than fragmented, siloed efforts. And again, it enables cross-domain collaboration, open infrastructures, fosters collaborations between hospitals, natural domains, startups, industry, and basically we lower the barriers to entry. So just to close this, to conclude, in healthcare, all these 6 components that I mentioned here mean faster translation from research to patient care, which unfortunately we are still far from having this model used in the actual care. Thank you so much. I believe we still have a few minutes left for any questions. And I would like to say thank you to all collaborators for making this work possible across different institutes, my university, also Vector Institute, and also University of Toronto. Please, this barcode takes you to our OpenPMC Hugging Face. The data set is, as I mentioned, publicly available, the GitHub, the source codes, and everything. Thank you so much. Any question? Yeah, please. Yeah. Yeah. Are you in the healthcare domain? Do you work? Oh, okay. Yeah. So are you talking about, so basically like health data is digitized, right? I assume that even in Portugal they have EMR systems, right? So for clinical practices, I guess like this EMR is somehow the data, at least for that region, like they make the data kind of the views that they have, like it works for clinicians, right? But are you talking about AI, like making those data ready for AI? Okay, that's a great question. And basically, there are some common data framework, HL7, and also OMOP for observational data that basically, like when it comes to within healthcare, data is in different modalities. So I assume you talk about electronic medical records, right? Like patients' data captured, like the vitals, the medications, and so on. So like these data, like we are talking about longitudinal time series data that are captured, at frequent time points. For example, a patient stays in the hospital for 3 days, another patient stays in the hospital for 5 days. So basically like common practices that we currently do in North America, and I assume that's the case in Europe as well, is we try to we get access to the backend, the EMR data, and then we transform them into those common data framework. And basically like this is, and then like Mimic, if you go like Mimic is an EMR data from Boston Hospital, like they also have this common data framework. With this common data framework, each column has a unique name, and we make our AI models for diagnostic tab. What is the mortality risk, or like the risk of readmission? These are the things that clinicians are very interested. So we make these AI models based on those common data framework. And I highly recommend following those standards. So the EMR itself, like transferring EMR, it has its own standard, and for observational data, it has this OMOP framework. Okay. Any other question for me? Okay, take it as no. Thank you so much. Thanks. Thank you.